This session is creating a spider goat using transactional memory support for security. And this will be, your speakers are, and I'm probably going to say this wrong despite the fact that you've corrected me twice now, Igor Mutic.
That is right. Thank you, Ricky. Okay, hello everyone, and thanks for making it to the last session of the day. We have a very good hour in front of us, and it's the last hour at Black Hat. And after we are done, we will be able to relax and enjoy ourselves and have even more beer and think of going to DEF CON and all that exciting stuff. But I'm hoping to excite you here today with some interesting research that we've been doing. As Ricky mentioned, my name is Igor, and I have two co-authors for that research, Alex and Roman. Alex is on his way from the airport, so I'll take all the brunt and deliver the speech. He might show up at any moment in time, but this work is joint, and I am presenting it. So the first thing I ought to do is actually explain the title. The title, it's weird, but then again, if you saw a more boring version of it without any genetically engineered animals, just plain using transactional memory support for security, it wouldn't be as interesting, potentially. And why are we talking about genetically engineered animals anyway? We took some technology available in contemporary CPUs, stuff related to performance improvements mainly, and applied that to security. It's not something that is often possible or that can normally be done. So it's a bit of an unusual animal, and it has its quirks, which we'll be discussing in some detail later. And that's why we were trying to come up with a good name for it. And the first thought of a genetically engineered animal that we had was a spider pig. Can I ask you, by the show of hands, to show who knows what a spider pig is? Okay, 1, 2, 3, about half of the audience. Okay, so let me, for those who haven't seen a spider pig before, show you a famous cartoon from Fox, Simpsons movie, and that explains to you what a spider pig is.
Great, but the very best thing is that he listens to you, because nothing means more than for a man to... How did the pig tracks get on the ceiling?
Spider pig, does whatever a spider pig does. Can he swing from a web? No, he can't. He's a pig. Look out, he is a spider pig. Okay, that was a YouTube video of that part of the movie, and so now we all know what a spider pig is. But spider pig is actually not something used for security. And we were thinking, what other animals are good animals that are often used in security? And such an animal is a goat. I'm not sure if all of you know what a goat program is or goat process. It's a concept of very primitive honeypot, essentially. You take something and you leave it to its own devices. Usually, some predator chases that animal, like a wolf in this picture. It attacks the goat, and then you know that animal is a predator. And that's how we often applied goat programs, goat files. You leave it in the system. If it changes, something must have attacked it. So that's a security concept embodied in a goat. We combined these terms, spider pig and sacrificial goat, and came up with the spider goat. So that's what we are going to talk about. And I have some visual aids here, horns, like a goat horns.
and we'll be using it in our future explanations. So here we are. Our agenda today is to discuss monitoring memory. Monitoring memory is important because when you want to know if something is making unauthorized modifications to kernel system tables or system dispatch tables, it's all usually done with some nefarious purpose. So you need to know what changes in memory, why, and full memory access controls are not really something that we currently have. So all monitoring tools for memory and technologies suitable for that are potentially very useful for security. And we'll see what's available right now. Then we'll talk about transactional synchronization problem. If you don't know about that, not to worry, I'll explain it to you in simple terms. And then we'll discuss what the solutions are for transactional synchronization. Hardware solutions. These hardware solutions we would want to apply for security, which is something that's normally not done, and that was the purpose of our research. I'll show you a demo of how unauthorized memory changes get detected by using transactional hardware support. And we discuss potential applications of these technologies and what are the advantages of using it and also disadvantages of using it. And at the end, we'll compare all the memory approaches, standard ones and the new one, sort of in a table, one-to-one, and see what the strengths and weaknesses of each one is. So the simplest way of monitoring memory for changes is just running a tight memory checking loop. You keep reading whatever you're interested in and comparing to what it should be. The problem is that if some malicious code tries to modify these areas of memory or patch the checking loop itself, you may not even have time to react, and that type of software protection will be fairly easily defeated. It's also very CPU intensive, so pretty expensive from the point of view of consuming CPU cycles and battery in laptops and all the drawbacks associated with it. There is another method which can be used from the hypervisor mode, and if you're in control of memory page tables, you can declare some of the memory pages as read-only, and then any attempt to write to these pages would naturally create a page fault, and that exception can be caught, and you can check what part of the page that you labeled as read-only was modified. But to be able to revert the changes or make comparisons, you need a full copy of the page. So if you protect many, you would end up having an exact copy of what you are protecting somewhere else, which doubles the memory requirement. And that's expensive. And also the disadvantage, of course, is that you have to apply these checks from the hypervisor or from the operating system, who are in control of page tables or extended page tables. Another disadvantage of paging technology is that the granularity. One page is 4 kilobytes, and that's a pretty large blob of data. If you know that something modified 4 kilobytes, you still have to go inside and check what exactly was changed in this particular page. So that's the arsenal that we have now. And by the end of my talk, I'm hoping to show you one more tool that you would have at your disposal to constantly monitor for memory changes, and there are some clear advantages in doing so via transactional support. So let me explain to you how that hardware technology came about and what the transactional synchronization problem is in the first place. It actually came from the area of databases. Basically, when several programs or computer threads want to modify the same area of memory, the same record in a database, they may create a conflict. If both write to the same location, this access has to be arbitrated. And that's how it looks. In database, this scenario is very, very often happening. In this example, if we have one user, Alice, and she has $1,000 in her account, and two database threads want to add one $100 and another $50 to the same account. Depending on when they read the original amount, increase it and write it back, depending on the order of these events, you may actually end up having very different outcomes of that operation. And in total, you would potentially have 3 outcomes. Only one of those is correct. To solve that problem, typically software is using locks. So basically, if one piece of software wants to modify an area of memory, they put a lock on it. It's like a semaphore. It can be red or green, and other threads wait, which is extremely bad for multi-core CPUs, because other cores essentially stall and wait for the first core to complete the operation. That's waste of hardware, if you will. And the origin of this problem lies in the fact that if 2 separate programs or 2 separate threads write to the same location in memory, a read-write conflict can occur, and arbitrating this conflict is the root of the problem. Let me explain to you how typically locks are used in software. As I said, Alice, let's imagine, has $1,000 in her account. Then a thread comes about which wants to add $100 transaction transfer from Bob. And that transaction should add 100. So to make it safe, that thread puts a red lock onto that memory cell so that all other processes in the system would wait. Then the transaction is complete, 100 is added. Alice ends up with $100 more than she had. And at this point, the lock can be released, and it's again a green light. Another transaction, which potentially was waiting for the lock, checks it's green, and Carol wants to add $50. It again locks that particular memory area, that red semaphore, performs the transaction. Now the amount of money in Alice's account is correct, because it occurred in exactly the right steps, and there was no interference from unsynchronized reads and writes. And then it can be released for all other transactions which were potentially waiting, whether they were running, waiting, or not. That situation is bad for multi-core CPUs. And that's why hardware manufacturers were looking for a solution to this problem. The transistors get smaller, the CPUs get more powerful, and you want to run them at full speed. And waiting for a software lock to be released to perform computation and addition is just not effective use of hardware. So the idea was you let that hardware run, and you let it make mistakes. And if a mistake happens, the hardware should only be able to detect it. And then the software kicks in and fixes a hardware mistake. Did you get that? So the idea of transactional memory is that you let hardware run and make mistakes. There is a hilarious explanation of that technology in a Usenix post from one of the Microsoft guys. Mickens is his name. And he was writing there that as hardware is getting smaller and smaller, you just allow the computations to go ahead, and if they produce an error, you re-execute them. And he also writes that modern software barely works when the hardware is correct. So relying on software to correct hardware errors is like asking Godzilla to prevent Mega Godzilla from terrorizing Japan. In the same blog, there is another statement from the same person, and to be honest, it has absolutely nothing to do with our topic and transactional memory and using it for security, but I wanted to quote it anyway because it's one of my favorites. It says that if CPU utilization on a computer goes above 4%, the computer either has a virus or the user made a disastrous decision to run Java. I thoroughly recommend you reading the entire blog post because it's just a lot of fun. But the main idea is letting hardware to execute and trap if an error, like a real read-write conflict, occurs. And the realization that it would actually speed up computations, and some modeling was obviously made, was achieved several years ago, and the first hardware with this capability came from IBM in Blue Gene computer in 2011. Then they released the mainframe in 2012, ZEC12, and Intel released the fourth generation CPU called Haswell in summer 2013, and that is what we have been experimenting with. IBM also released Power Rate CPU just a little more than a month ago in June. And all these CPUs have transactional support. So separate threads can start writing to the same location, and there are mechanisms to resolve these problems if there is actually a conflict. Intel Transactional Synchronization Extensions, it's called Intel TSX, is basically an optimization which is focused on resolving threads conflicts. And it comes in two kinds. There are two methods of introducing it into software. Hardware lock elision, or HLE. And another is restricted transactional memory, RTM. They achieve the same goal, but through slightly different level of compatibility. HLE is more easy to put into your program, but it doesn't give you full flexibility. RTM gives you full flexibility, but you have to make more changes to the software to perform your transactions and detect conflicts between threads. So in lock elision mode, there are two new instructions, X-acquire and X-release, these two. And they're actually not instructions, they're prefixes. So old CPUs just skip them, they don't understand these prefixes, they are new to them. And that provides full 100% backward compatibility with all the CPUs. In RTM mode, there are new instructions. They have separate new commands, and executing them on any CPU that doesn't support them would create an illegal instruction. So before doing that, so before executing XBEGIN and XEND, these new instructions for transactional support, you have to check that the CPU supports it. And the CPU ID check is written in the bottom line on this slide. And by interrogating the CPU capability, you can learn whether it supports restricted transactional memory or not. And there are a couple of auxiliary instructions, XTest and XAbort, to facilitate sort of the plumbing related to transactional memory. So let me show you how the code looks like when you write software with locks. That's a standard, usual way of doing it. You have a lock in this variable. You read it. If it's okay, you just go and add your $100. It's safe to do so. If it's not okay, you keep reading, spinning in this small loop. And once the lock is released, you return, try to obtain it again. And once you obtain the lock, you safely add $100. Simple. So in hardware lock elision mode, all you have to do is just add one simple prefix, which is execwire. What it tells CPU to do is to go, do this transaction. Don't really care about the value in this mutex value, the lock. But if somebody else writes to the same memory that your transaction, which starts with this execwire and goes all the way until you use X release, if something writes to the same location, CPU would come back to that point and do the same thing again, but only without that transactional mode. So essentially, it reverts to the previous behavior after trying once. In many cases, that actually produces a hell of a performance improvement. But in restricting transactional mode, you can do a lot more. You write a whole new routine, which speculatively adds $100. And if that writing created a conflict, which is called an abort, and the abort location is specified in the first instruction, XBEGIN and the abort. Abort instruction, abort is the offset of that routine, and it handles the conflict. And it has full software flexibility. It can retry that transaction several times, as many times as it likes. If it fails, it can go and repeat that transaction in the standard mode, just like this. But in many cases, it will succeed, so that's fine. You can read about that more. There is nothing new to it. I'm just giving you the background about transactional memory in Wikipedia, and there are many references there. If transactional memory approach is successful, what happens is that instead of cascading and locking the same memory area between different threads, so that thread was waiting for the first to complete, then the third one was waiting for the previous two. It executes sequentially. With transactional method, you can execute them in parallel, and in most cases, the conflict wouldn't really occur. The threads write very quickly, so if they complete the write, the next transaction wouldn't actually create a read-write conflict. It would just get the new updated data. The most common question about Intel TSX is, so what is that technology? Is it related to virtualization? Or maybe it's some variation of page protection technology. And I wanted to state up front that Intel TSX is not related to virtualization at all. It has nothing to do with page tables. It's a completely new functionality in the CPU. And it actually piggybacks on how the CPU processes accesses to memory through cache. So the granularity of these accesses is the cache line, 64 bytes. And transactional memory can detect conflicts within cache lines, but it cannot detect with better granularity. So inside 64 bytes, what exactly was the conflict place is not visible to the programmer. Transactional memory support in the processor has its own dedicated memory to store a table of which accesses have occurred. And it uses existing cache coherency protocols to detect conflicts. Because it's existing cache systems, it works between different CPU cores. It works with different hyperthreads in the same core. And what actually happens if a thread is executing as a transaction and writes to a place in memory, before that thread completes a transaction, which is denoted with XEND instruction, that write is not visible to the rest of the system, which means essentially the CPU is executing these memory writes as a sandbox. And with a sandbox, we can do quite a lot of interesting security things. In normal mode, we require programmers to mark transactions in source code, and they need to resolve a conflict if two threads conflicted by one doing read, another doing write, or both doing write to the same location. The programmer has to resolve that problem, like we saw in the example. In the worst case, one has to revert to a standard locking mechanism. And the method to resolve that conflict is by specifying the abort routine, the offset in the XBEGIN parameter, which gives you the place of the code, which looks at the results of the conflict, and it can resolve the transaction conflict. The programmer may rerun that transaction several times, and in the end, if nothing else works, software logs will. So let me show you what the typical Intel TSX use is. On this slide, we have two threads, the first one and the second one. They execute in parallel, and there is a piece of memory in the middle between them. And we want to detect when this read to that cache line B occurs, while that write to the same cache line B in memory already performed the modification. So I'll need my visual aid. In this case, both transactions have XAbort parameter. One specifies the abort handler for this thread, another specifies the abort handler for this thread. So we have two. So let's execute these threads in parallel. They perform both reads of the same location. They're both reads. There is no conflict. Then the next operation comes. Again, they read from another cache line. Both reads, no conflict. But both transactions actually remember which memory locations were accessed, read, or written into. On the next step, second thread performs the write, but to a different cache line that we are looking at. On the next step, again, one is performing a write to a location which is never accessed by the first, so no conflict neither now nor later. At this point, the second thread reads from the same location which is about to be modified by the first thread. And on the next step, the write occurs. And that creates a conflict because this memory location was previously read by a different thread. So at this point, immediately, the CPU in hardware generates a CPU abort. All the memory changes that were done by the second thread, all these writes to locations D and C are reverted, and they were not visible to other threads in the first place. And the abort handler associated with that thread receives control. So that offset 2 receives control. That is typically how TSX is working in standard mode. So can we use transactional memory support for security? It was implemented to make database software more performant. And with all due respect to programmers of database software, the million-dollar question is whether that technology can actually be used for something more burning, like security. So let's have a look at that. We do a very similar script with the only difference that now we want to protect these two memory locations, A and B. So two cache lines, you see that spider goat in here, protecting them both. And that's the memory regions that we want to monitor. So our thread, the first one, security assistance thread, is constantly reading from these locations. And what you can notice is that that thread doesn't have XBEGIN instruction. So it's not executing as a transaction. But that asymmetry in TSX implementation is allowed. And if there is a conflict, read-write conflict between any thread and this transaction, then an abort would happen. So with the help of the video aid, we have now one transaction executing with abort here and another without an abort. So let's run through that. Both threads do a read. Even though it's from the same cache line, it doesn't matter, it's a read. The security thread is only doing reads, mind you. It will never do any writes, so it's only interested in creating artificially a conflict with what we consider potentially malicious thread or suspected thread. And that suspected thread does a write to a different cache line, called D in this slide, then to C, and then to B. B is what we want to protect. So at that point, we see that this cache line is marked red at that point, and any subsequent access to that memory cell or cache line with the security thread to the same location will create an abort. So it instantly created by the CPU. All the memory changes that were done by, sorry, wrong button. Let me roll it back. Yeah, that's where I should be. So at this point, an abort happens. All the memory modifications which were performed by the suspected thread are reverted. And the control is transferred to the offset defined in this XBEGIN, abort offset 2. Now, of course, you would probably ask a question, how does XBEGIN ended up in a suspected thread? Normally, it's not an easy thing to do, and if it's malware, for instance, doing some modification to the kernel memory, you have to get a suspicion and inject that XBEGIN to do the memory reversal. But you can execute the same transaction in a slightly different way. If you don't inject XBEGIN into a suspected thread, you can still detect changes that it's doing to what you protect, only without memory reversal. And that's done again with asymmetrical launching of transactions. You have security thread defined as a transaction. And the suspected thread now does not have XBEGIN. So that means when an abort will happen, that thread would execute its abort routine. And this abort routine, as it's not doing any writes, will have nothing to revert in memory. So we have a visual aid in a completely different situation. We have XBEGIN in one thread and no XBEGIN in another. Moreover, because you do only reads in this thread, you can do it once. They are placed in the transactional buffer. And the fact that these lines have been read is remembered, and once the first write occurs, an abort would happen. So that first security thread can just spin here without actually repeating the reading. And as soon as suspected thread writes to that particular cache line, we get an abort. Only in this case, there is no memory reversal. So by putting XBEGIN in either security thread or into suspected thread, so doing XBEGIN either this way or that way, we can control whether the memory reversal on the writes done by suspected thread is done or not. So let me show you now a live demo of how that technology works in an Intel TSX capable notebook. And I had to drag all that big Lenovo professional laptop all the way from England instead of my usual Ultrabook, and it's a heavy beast. But it does have the latest CPU, and it does support TSX. If you, by the way, want to play with TSX at some point, you have to be very careful about selecting the hardware specification, because not every laptop released after 2013 will actually have it enabled. So the CPU can execute million instructions in just a fraction of a second. So the demo is artificially delayed. Each and every memory read and write has a sleep for like 1/5 of a second for you to be able to see something. And I'll show you two systems in sort of one program, one legacy, and one with TSX support. It wouldn't fit completely on the screen, so I'll show you it in some sort of a window. There will be control buttons. One is called run safe code, another run malicious code, and another turn on TSX protection. So let me do that. Right now, I turn to my desktop, and I have a program here called TSX demo exe. And here it is. On the left side, it's part of a program which is not using TSX in any way, shape, or form. And what it does, it has the code area, the data area, and the area we want to protect, like system call table, as an example. There is a message area at the bottom, and you can basically do only two things: run safe code or execute malicious code. So let me press running the safe code. So safe thread is executing, and it's reading from code area and data area pretty much randomly. Now it's finished. Now I run malicious code. Malicious code is running and writing some data into memory. And now it wrote into the system call table. Message window shows that system call table has been corrupted by the malicious code, and malicious thread is finished now. It's all done in software. You just call piece of software which is writing to our imaginary system call table. It's not a real one. It's just a blob of memory. So that malicious thread wrote to that particular part, and we call it malicious. So let me switch it to the right side, where we have part of a demo which is using TSX support. At the beginning of this piece of the program, it checks that the CPU is TSX capable, and it shows that in the message window. So now I will just start the protection path, that big blue button starts a security thread, and it starts reading from the protected area, which is the system call table. And it's monitoring it, reading and reading. It does nothing else. It doesn't actually read and compare with what it should be, just fetch. And now I press malicious code. malicious code starts executing, writes to some places in the code area, and now it wrote to one location in the protected system area. Now, the conflict will occur when our blue thread reaches that point. When it reads from the written location, you can see that here in the message window, we had an abort, and that abort showed that the read-write conflict has been detected, and the memory change was actually reverted back to what it was before. So that's a demo. It really runs on a real TSX. And okay. And what could be the potential applications of this technology? The first idea that comes to mind is using it in the kernel and the operating system, like VMM and OS vendors, to protect kernel or kernel code or kernel data. And PageGuard can potentially use it to perform self-protection. If something is suspected, you can start monitoring that suspicious code. So inject XBEGIN, execute an abort routine if your suspicion is confirmed that the suspected thread actually did write to the location that you are monitoring. And you can apply it to protecting any critical code or data, like system call table, but anything really. Outside of these areas, it can be used by any independent software vendors for software protection. And you, again, can protect your data or your code from modification, patching, and I mean in memory. It definitely raises the bar for the attackers, because if your software is doing self-checking and self-protection via TSX, the attackers would have to figure out what is going on, because it's something that normal attacker wouldn't expect, that hardware-supported exception or abort happens if modification occurs in a particular place that was protected via TSX. The advantages of this technology is that essentially it creates a very short-lived, hardware-supported sandbox, and you define the shape and size of that sandbox. Your security thread, when it starts reading from memory, it can actually create a sparse pattern or contiguous block of memory, and by keeping reading from it, it'll define what is protected. And as soon as some suspected thread writes into any of these cells, or cache lines, hardware-supported abort will happen. The granularity of protecting memory is 64 bytes, which is way, way better than page tables. 64 bytes versus 4 kilobytes. And what's probably most important is that it's instant reaction of hardware. If any malicious thread wants to write to a particular location, like modify security software, for example, that is running self-protection, it will not have any time to do so, because the reaction is instant. There is no chance to explore any type of race condition and modify security software while that thread is suspended or inactive. The abort will happen instantly and can be reacted to instantly. And if you correctly put XBEGIN into a suspected software, you can also revert the changes. Or rather, the CPU would do the changes, reverting for you. So, is it all nice and shiny? Not quite, because there are some challenges with this approach. And when we were experimenting with it in a real operating system, what we noticed is that the operating system is creating a fair amount of noise. Transactions, they're supposed to be fairly short. That was basically the design requirement for supporting this optimization in database software. And you can run thousands of instructions or several thousands of instructions. That is very quick. But in operating systems, there are interrupts, there are context switches, and every single one of them completely terminates the transaction. That is by design. The transactions are all aborted if an interrupt or context switch occurs. And in the abort handler, you can actually determine the reason for the abort. And unfortunately, that noise in the operating system is fairly significant, and timer interrupts, switches between different processes are frequent. So to perform effective protection via TSX, your threads should be fairly short, and while they're executing, you should be able to start another thread, which is also short, and if it's interrupted, you can create another one. But it's a little trickier than sort of the type of protection provided by page tables, for example. If you want to do memory reversal, you would need to inject XBEGIN into a thread that you suspect. That is not normally easy, and you would probably require hypervisor support to do injection into other processes. Memory reversal is not an easy thing to do. And obviously, if malware is operating in kernel or in hypervisor and already infected the system, you're fighting against it. The transactional support wouldn't give you any immediate advantage, because any kernel software can disable transactions and stop any software that is executing security threats. And another problem with transactional system is that each CPU core has its own dedicated transactional memory. So it keeps track of what was written and what was read, so that it can match it via coherency protocols with all other cores and detect conflicts. But that capacity is limited. On Haswell CPUs, currently it's 32 kilobytes and maybe slightly more than that. But if you know what you are doing, you can fairly easily exhaust these buffers and cause denial of service by running just bogus transactions, and that would create capacity aborts, which you can also determine when an abort happens. The reason, was it a memory read-write conflict or a capacity abort? Attacks on cache and exhausting cache are well known, and they all apply to transactional buffers as well, because they are piggybacking on cache. So if we write a table which is comparing tight memory reading loop, page-based protection, and transactional memory type of support, and evaluate these memory monitoring technologies on several different levels, we can see that the tight memory loop runs in software, while page tables and TSX actually have hardware support. The granularity of tight loop is very good. You can get down to 1 byte or even check bits in it. Page tables are pretty bad with 4 kilobytes granularity. Transactional support gives you 64 bytes, which is sort of something in the middle, and that is much better than 4 kilobytes. To run these, the tight memory loop can run anywhere, hypervisor, operating system, in user mode. Page-based stuff can only be written in hypervisor or the operating system, but transactional system can be used anywhere. You can use it from user mode. In fact, it's a CPU capability which would work in real mode, in 16-bit CPU mode. It really doesn't care. And that's a nice feature, because in user mode, any software can perform self-checking You run two threads, one checks another through transactional support if CPU is capable, and that provides additional software protection. The speed of operating these methods, it's very slow in tight memory loop, and even if you read the same byte constantly, it still may not be quick enough if malware disables the checking thread. In page-based exceptions, you still have to read the page, analyze what was inside modified, so it's sort of medium type of speed because you have to do some software checks on top of hardware-supported page exceptions. And with transactions, it's sort of in the middle, but it's faster than the pages. With transactional memory, unfortunately, you cannot cover a lot of memory. You may be able to extend it to several megabytes of memory, but the more you cover, the more often you will see aborts related to capacity because, well, more writes would fall into that area, so the buffers related to transactional monitoring will be exceeded quicker. And probably the biggest problem with transactional support is that it's short-lived. You cannot just let it run and hope that in 10 minutes it'll create you a hardware abort on the memory that you're monitoring. It's very short-lived. It was designed this way. And as conclusions, what I showed you is a bunch of methods that use transactional memory for things that it was never designed to do. So it's a new tool in your arsenal as security practitioners, and that would allow you to perform software self-protection, modify operating system sort of resilience, like PageGuard, for example. And it's a fairly unusual and novel security method because it was not designed for that and nobody before thought of using it for security. Because it was not done for security, the whole technology is a bit quirky. When you start using it, you will find that these operating system caused aborts, noise type from interrupts and context switches are actually fairly unpleasant if you want to monitor for a long time. But for software protection, it's fine normally because if you have a thread to protect, you know its lifetime. You could spawn another one and do the self-checking in between. And that is a result of our genetic engineering. We have a fairly strange beast, spider goat, which is based on hardware capability, but is helpful for security and helpful for software protection. The research on this stuff is ongoing, and we are experimenting with it a little bit more. And if we find something interesting, we would be very interested in sharing it with the rest of the security community. And that concludes what I had to say. So if you have any questions, I'd be very happy to answer. There's one question over there.
For the memory protection 4K, you kept on saying that one has to check all the 4K, all the 4K. Is that what you said?
Well, if you mark a page as read-only, and the write is performed into that page, then you have to analyze where exactly that write was going. And another way is to let me rephrase your question.
So I don't see a problem with 4K. I mean, you get an exception, you know exactly where the write happened, just immediately you know. And if you want to know what, You simply decode the instruction and you figure out what is being written and so on.
Mm-hmm. Okay.
I mean, it's not expensive.
Well, the expensive bit comes from reverting the change, because if you want to put the data that was there before, you have to keep the whole 4 kilobyte page somewhere else.
Yeah, but I don't do that. I put it read only. Somebody wants to write. If I want to allow the write, I let it write. If I don't want to allow it to write, I simply don't. It won't even write because it's still read only. So I don't have to save anything.
Mm-hmm. Well, the situation will be different if you allow the write and then you analyze what happened after the write.
Then if I allow the write, then I won't have exception. If it's page read write, then I won't even have this guarded page anymore.
Okay, let's dig deep into that after the talk and come over and let's talk about it.
And about the 64-bit, 64-byte, what does it mean exactly? Like, once I read from a certain location, that means it will be round to 64 bytes, and then this whole area around the 64 byte will be protected? Or can I, like, say, protect one piece here, one piece 2 megabytes further? How does it work?
Well, it works based on cache lines, so 64-byte granularity. Any read of a byte from a 64-byte area would mark the entire cache line as accessed.
I see.
And if you are at the end of this 64-byte area and do a multi-byte write, it will overflow into the next one and mark 2 cache lines. Did it answer your question?
Yeah. And one last question. What prevents the attacker, the first thing he does, calling XEND, and then does whatever he wants to do? He will just kill your security thread immediately. So if he wants to touch sensitive areas, call XEND, do whatever you want, and...
Well, in principle, the attacker can, but to be able to issue XEND, they first need to determine whether the CPU is actually RTM capable. So run CPU ID.
Yeah,
and
fine.
If you have a supervisor running in hypervisor, you can intercept CPU ID and detect that the particular process is interested specifically in RTM capabilities and treat it in some special way. But yeah, you're quite right. Actually, without XEND, it can also perform XTest, which checks whether the transaction is in progress and then behave differently. So in that regard, it's not really very different from where we are now in analyzing behavior of malware.
Yeah, so in that case, for software protection, it's not going to be useful at all. Simply check if TXX is available, remember it somewhere. You want to touch areas as a hacker, just call XEND. And you're done with this. So it kills completely the software protection vector.
Well, it's not completely useless, because if you have a scenario, for example, when you suspect some piece of code to be shell code, but you're not sure, then you can mark some areas that you suspect this piece of shell code might be writing to and keep monitoring them. If the write does happen, then you know that particular shell code was actually real shell code and not just your false suspicion.
Okay, and last question. So now I have to have a thread that is continuously reading and reading and reading, right? So that also consumes power?
Well, in the second slide that I showed, when you make a security thread, a transaction, like one of those two, you don't have to keep reading. You can read just twice and then do something useful. Unfortunately, in transaction mode, you cannot do much of useful stuff, because practically any operating system API would abort a transaction because it will cause this or that type of context switch eventually. And even the CPU pause command causes an abort. So you are limited to what you can do inside the transaction without actually aborting it. But still, some computations are possible.
Okay. In the case of when you do while one? Yeah.
Thank you.